Good morning, everyone, and welcome to class. I wanted to begin with a little thought from Heber J. Grant: that which we persist in doing becomes easy to do, not that the nature of the thing has changed, but our power to do so has increased. And I really like this thought for Chem 106, especially because you guys are learning lots of new things, and many of them are not easy. And they don't suddenly become easy for no reason, but you, through your diligence and your practice and persistence, can become much better at doing them. So I encourage you to remember to practice, get help when you need it, make sure that you do lots of problems and that you understand how to do them and can explain them. Okay, let's get started. Today we're going to be talking about rates. So our goals are going to be to talk about average versus instantaneous rates, how we calculate the rate of reaction using average rates, and then also to talk about collision theory and factors that will affect the reaction rate. Why do we care about chemical kinetics at all? We call it kinetics, and this is studying the rates of reactions. And it's because it's important to know how fast things happen. PET scans, drug metabolism, how long will a drug stay active in your body, enzymes, lactic acid buildup, mineral formation, radiometric dating. There's a lot of things that happen at different rates, and when we understand how quickly those reactions happen, it can help us predict what we should do or how we should change conditions to have better control of the reaction. The other thing is, it's really important for us to understand how things happen or the mechanisms of reactions. Now, it's going to take us a few days to get to the point where we're talking about mechanisms, but everything that we're learning right now about kinetics is really leading up to that point where we'll be able to talk about how a reaction is happening or the mechanism of the reaction. Sometimes when we're dealing with rates, we have to look at things that are changing over time, and how quickly or slowly that changes often has physical meaning, and it's very simple to talk about the rate. We just take the change over time. So if we're talking about speed, we do change in position over change of time. And a shorter way to write that would be delta x over delta t equals v, velocity. The delta symbol here means change, so the change in x, which is the position, over the change in time. We're going to use that delta symbol a lot more often throughout this lecture, so just a reminder, that means change. And as an example, let's say we're taking a trip to Salt Lake. It's about 50 miles, and it takes about an hour. So if we look at our change in position over change in time, we know our average speed is about 50 miles per hour. Okay, so our average speed to Salt Lake is 50 miles per hour, but it doesn't necessarily mean our speedometer is 50 miles per hour the entire trip. Let's take a look at a chemical system and think more about why these rates matter. So we have, this is an example from your textbook, and it has to do with the production of photochemical smog. A lot of people, it turns out, are sensitive to ozone in the air in the lower atmosphere where we can breathe it. Ozone is good in the upper atmosphere because it protects us from UV light, filters out dangerous radiation, but in the lower atmosphere it can actually cause asthma and other respiratory problems. And if we look at the different reactions that are happening in the air, it turns out over time, because of the rates of these different formation of different products and chemicals, over time, it's actually the ozone levels that are the highest in the afternoon. So, for example, if somebody that's sensitive to ozone wants to go out running, it's better for them to do it in the morning rather than in the afternoon. And that can make a difference for their lives. So measuring the rates of chemical reactions makes a difference in a lot of situations. And it's possible to use any property of the reactant disappearing or the product appearing to measure the rate. A lot of times people will use spectroscopy, and pressure is an example of something that we can use. In experiment 3 in Chem 107, you guys will use pressure. Your data will actually look like this, where you'll see an increase in the amount of pressure as a gas is formed in the reaction. And in experiment 4, you'll use spectroscopy and you'll look at the disappearance of a reactant over time. And it doesn't matter which property you measure over time, any property that you can measure can be used to measure the rate of the reaction. Okay, so now let's look at a chemical reaction. We've got nitroethane. On the reactant side, it's forming ethene and nitrous acid. So if we have C2H4, we're looking at its appearance. We'll look at the change in the concentration of C2H4 over the change in time. And we would do the same thing for HNO2, change in concentration over change in time. Now what about the reactant? The reactant is actually disappearing. So if we want the rate of the reaction, we need to end up with a positive number. And so we'll put in this negative sign here. If it's a reactant, because it's disappearing, we put in the negative sign. That'll actually make the rate that we measure positive. So we'll have the negative change in the concentration of CH3CH2NO2 divided by the change in time. Now, what do we do if we have coefficients in our reaction? It turns out when we're doing these calculations, we're interested in the rate of the reaction, okay, which is a little different than looking at the rate of formation or disappearance of one of the products or reactants, respectively. And so we'll be looking for 1 mole of reaction. Now, if I have 2 moles of N2O5 in my reactants, to get a mole of reaction, I actually need to divide by the stoichiometric coefficient. Because 1 mole of reaction will use up 2 moles of N2O5. Likewise, 1 mole of reaction produces 4 moles of NO2 and 1 mole of oxygen. So in each case, what I'm going to do is I'm going to take the change in that substance divided by time. I'll keep my negative sign if it's a reactant, or I'll have a positive sign if it's a product. And then I'm going to divide by the stoichiometric coefficient. So in the case of N2O5, where the stoichiometric coefficient is 2, I'll divide by 2. So negative 1/2 times the change in the concentration over change in time of N2O5. If I want to do this for the other substances, my formation of NO2, again, this one will be positive because it's one of the products and it's produced in the reaction. But notice I'm dividing by 4 because the stoichiometric coefficient is 4. For oxygen, it's easy because the stoichiometric coefficient is 1. I don't have to add anything else. Okay, you guys, so now we'll have a Podia quiz. Here is the quiz question. I'll ask the TA to pause this for a minute or two. You guys work on it, and then I'll come back and tell you the answer. Okay, so the answer to this question is A. This is an incorrect rate expression because we're looking at the formation of the product, NH3, so it's correct that it's positive, but it hasn't taken into account the stoichiometric coefficient. The correct one would be D, 1/2 times the change in NH3 over change in time. Okay, now let's do a practice problem. If we look at this same reaction, the partial pressure of N2 falls by 35 torr in a closed vessel with nitrogen, hydrogen, and NH3 all present. And we have several questions that we have to answer. So what is the rate of change in the partial pressure of NH3? We know that the change in N2 is 35 torr per second. It's decreasing by 35 torr per second. What is the rate of change in the partial pressure of NH3? Go ahead and work with a partner on that. I'll give you about 30 seconds. So TA pause. And the correct answer for this question is 70 torr because the coefficient for NH3 is twice as much as the coefficient for N2. So it should increase by 70 torr. What is the rate of change in the partial pressure of hydrogen? Again, 30 seconds. TA, go ahead and pause it. And the correct answer for this one will be negative 105 torr, negative because it's one of the reactants, it's disappearing, 105 because it's 3 times 35. And final question, what's the rate of change in pressure of the entire vessel? This one's a little bit harder, so take about a minute or so to answer this question. TA, go ahead and pause it. And the correct answer for this one will be negative 70 torr. If we add up all of the changes for all of the substances that are in there, it turns out the pressure should be decreasing. Okay, another Podia quiz for you. Again, TA, you can pause this and we'll start it up again. And the correct answer here is D. Because N2O5 changes twice as fast as the reaction, we'll divide this by 2, the stoichiometric coefficient, to get the answer. We have one more Podia quiz here. Go ahead and pause it, TA, and we'll come back together in a minute. As a reminder, you guys, we know that the rate of the reaction is equal to all of these things, right? We have these 3 different expressions that we can use to talk about the rate of the reaction. We know the rate of change of N2O5. We can set that equal to this other expression because it'll be the same for the overall reaction, and we'll find the rate of NO2. The correct answer is D. Okay, now we're going to move on to talking about instantaneous rates. If we think again about our trip to Salt Lake, we have this curve that might represent our total distance traveled and the total time. Remember, we said we went 50 miles and it took about an hour. But notice the slope of the graph is changing over time. In fact, if we look at this first situation, we were maybe on the surface streets in Provo. We might have been going 35 miles an hour. And then there might have been a moment, just a moment, on the freeway when we were going 96 miles an hour. Please don't do that. It should be like 76 miles an hour or something like that because it's a little too fast. But we might have been going really fast on the freeway. Our average time is 50 miles an hour, but if we shrink the period of time that we're looking at, it gets to be either slower or faster, depending. And if we were getting a truly instantaneous rate, we would take the derivative. You might remember that from calculus. We're not going to do that in this class. As a note, on your smart work homework, if it asks you for instantaneous rates, you can use the tabulated data that they give you. You just have to choose the points on either side of the time that they're looking at. So if they ask for this time, you choose the 2 points on either side. You should be able to get the correct answer. Now notice here that the rate is changing over time. What's happening to the rate over time, and why do you think that is? Go ahead and talk with a small group here for about 3 minutes. What's happening to the rate over time, and what's happening at the molecular level that's causing it? So hopefully you guys realize the rate is actually getting slower over time, and that's happening because there are fewer collisions of the molecules. So let's talk about collision theory. In order to react, molecules have to collide with enough energy and in the correct orientation in space. And you may have seen these reaction diagrams before where we have reactants and we have products. We can see the difference in energy between the reactants and the products. And also there's this part in the middle where they have to actually gain energy in order to be able to react and form products. Now, every collision that has enough energy to get up here doesn't necessarily automatically go over to become products. That's why we call this the reaction coordinate instead of time. Sometimes the reactants will collide and they'll have enough energy, but they don't have the right orientation, and so they'll slide back down to the reactant side. Sometimes they collide and they don't have enough energy, and so they can't quite get over that activation barrier. We call this hill the activation barrier to the reaction. And so all of these things, 3 things, have to be satisfied in order for the reaction to proceed and produce products. This is an example on the bottom here of a type of reaction that you'll learn about in organic chemistry. It's called an SN2 reaction, but essentially, in order for this reaction to work, this nucleophile is going to attack the carbon atom, but it has to come in, this is a tetrahedral carbon, it has to come in sort of uh, in the bottom of that tetrahedron between these three things. It has to approach from a very particular angle in order for that reaction to occur. And actually then that starts to form a new bond with the nucleophile, and the leaving group is going to detach. So this right here would be our activated complex or transition state, which is what's at the very top of this hill. And then the leaving group leaves, it's separate, and the nucleophile has a new bond to the carbon. And these X, Y, and Z groups have actually flipped around. So it's like you took the tetrahedron and flipped it around the other way. This is an example of a reaction where the orientation is a very particular requirement. It has to react in a very specific orientation or the reaction doesn't happen. And some reactions have specific requirements like this, and others, you know, if you just have two atoms and they're forming a new bond, they're making a diatomic molecule, well, that'll probably happen without too much difference based on orientation. But the more complex the molecules are, the more the orientation matters. And this can be especially true when we start talking about biological reactions where biomolecules are very large and complex, and the orientation, the chances of the molecules being oriented in just the right way is so low that the reactions essentially don't happen without help from enzymes in our body. Okay, so let's look at some factors that affect the reaction rates. We have concentrations, temperature, catalysis, and physical states. Okay, now we've just talked about collision theory, and I want you guys to take a few minutes talking to your neighbor and talk about each of these factors, the 4 factors. Physical states, by the way, means if it's like a solid, liquid, gas, etc. I want you to talk about each of these 4 factors and decide what parts of collision theory, so colliding with enough energy and in the right orientation, what parts of collision theory are affected by these different things if we change the concentrations, the temperature, catalysis, or physical states. So TA, go ahead and pause this for a minute, for a few minutes while people have that conversation, and we'll come back together soon. Okay, I hope you guys had some really good discussions. I'll just review some of these. So if we change the reactant concentrations, if we increase the concentration, there will be more molecules around in the same volume, which means they're more likely to collide with each other, so we change the number of collisions. If we change the temperature, we actually are affecting a couple of things. Because the molecules are moving around faster, they will collide more often. The other thing is, though, remember temperature is a measure of average kinetic energy. If we raise the temperature, we're increasing the energy of the particles, making them more likely to be able to overcome this reaction barrier when we look at the reaction diagram. What about catalysis? So catalysis is a unique thing, and this is where you have a catalyst, which is a helper molecule that makes the reaction happen more quickly. In biology, these are enzymes, although we can also have catalysts like inorganic molecules that act as catalysts, or metals that act as catalysts. And what they do is actually lower the activation barrier. So this red line here represents what would be a catalyzed reaction pathway. It's a little different than the pathway that they would do all on their own. And the reason it's different is because catalysts will orient the molecules in a specific way. This is especially true when we're talking about enzymes. They have an active site, and the molecule will stick into the active site in just the right way so that it's oriented in order to do that reaction. That ends up lowering the activation barrier. So because they're affecting the orientation, they also change the energy. The last one is physical states. Reactions in the gas phase are going to be a lot faster than reactions in a solid phase. Um, and the difference is just the number of collisions that are happening. If you have a chunk of something, only the molecules that are on the very surface of it are going to be able to react. So the reaction will be a lot slower than if you have a larger surface area or if it's dissolved or something like that. Okay, we have a Podia quiz here. What would you expect to happen to the reaction rate if we increase the concentration of hydroxide, or in other words, increase the pH? So go ahead and select your answers here and talk about it with your neighbors. Just 30 seconds to work on this. Tia, you can pause it. And hopefully you guys got the right answer, which is the reaction rate increases because we're adding in more molecules of reactant. They'll be more likely to collide with the CH3Br molecules and make the reaction happen. Okay, another quiz. What would happen if we added more solvent? Again, 30 seconds to select your answer here. TA, you can go ahead and pause. Now, because the concentration will be lower when we add in solvent, there will be fewer collisions and the rate will decrease. So go ahead and take a moment right now and answer these two important questions. Write them down for yourself. Take a couple of minutes to do that silently. How do you account for stoichiometry when calculating average rates? What is collision theory and how does it help us understand rates of reactions? So when we are talking about calculating average rates, sorry there's a typo, you guys. I don't know why, because I made a mistake, that's why. Um, when we're talking about calculating average rates, we account for stoichiometry by dividing by the stoichiometric coefficient of the thing that we're measuring. And we can also account for something being a reactant versus being a product with a negative sign. We do the negative sign on the reactants because they're disappearing. So when we put in the negative sign, that'll make it a positive number for the rate of the reaction. Okay, and collision theory tells us that in order to react, molecules have to collide with enough energy and in the correct orientation in space. And that helps us understand the rates of reactions because we can start to think about how different changes that we make to the system would affect the number of collisions or the energy of the molecules or the orientation of the molecules. And that can help us have better control over the reaction. Okay, you guys, that's everything for today. Thanks for coming today, and I hope you have a great day. I'll see you soon. Goodbye.